Welcome back to our channel to discover the next interesting things. The steel factory, a bastion of industrial prowess, orchestrates a complex symphony of metallurgical processes to transform raw materials into an array of steel products, including cold-rolled steel coils, hot-rolled steel coils, galvanized steel, and electroplated steel. The journey begins with the handling and preparation of raw materials, predominantly iron ore, coal, and limestone. These raw materials undergo meticulous processing to extract iron, a pivotal component in the steelmaking process. The heart of the factory comprises multiple units, each specializing in a specific phase of steel production. The initial step involves the blast furnace, a colossal structure where iron ore is smelted to produce molten iron. This process, known as ironmaking, involves the reduction of iron ore into molten iron through the reaction with carbon-rich coke. The molten iron, laden with impurities, is then directed to the next stage, steelmaking, where it undergoes refinement to meet precise specifications. The process of transforming iron ore into molten iron is a fundamental stage in the production of steel, epitomizing the principles of metallurgy and industrial alchemy. This journey begins in the blast furnace, an awe-inspiring structure that stands as a symbol of the steelmaking process. At the heart of this furnace, iron ore, typically in the form of hematite, iron 1 oxide 3, or magnetite, multivalentfe3014, undergoes a series of transformations to yield molten iron. The iron ore, along with coke, a high-carbon fuel derived from coal, and limestone, is charged into the top of the blast furnace. The purpose of limestone in this mixture is to act as a flux, facilitating the removal of impurities and promoting the formation of slag. As the materials descend through the furnace, they encounter intense temperatures reaching around 2000 degrees Celsius. The crucial chemical reactions within the blast furnace are intricately choreographed. The coke, rich in carbon, reacts with the oxygen in the air to generate carbon monoxide. This carbon monoxide, in turn, serves as the reducing agent, reacting with iron ore to form elemental iron. The chemical equations underlying these reactions are complex, involving the reduction of iron oxides to metallic iron. The molten iron produced in the lower regions of the blast furnace possesses high purity but still contains impurities, such as carbon and other elements. These impurities contribute to the overall characteristics of the molten iron, including its fluidity and temperature. Simultaneously, the limestone reacts with impurities in the iron ore, forming slag, a molten mixture of calcium silicate and other compounds. The slag, being lighter than molten iron, floats on the surface and aids in the removal of non-metallic impurities. The slag is periodically tapped off from the furnace, leaving behind the molten iron. The molten iron, now collected at the base of the blast furnace, is periodically cast into molds to form pig iron or directed into downstream processes for further refinement. The pig iron, though a valuable intermediate product, still contains excess carbon and impurities. To produce steel, this pig iron undergoes additional refining processes, such as the basic oxygen furnace, BOF, or electric arc furnace, EAF, to adjust its chemical composition and mechanical properties. The process of melting iron ore to create molten iron in the blast furnace is a testament to the intricate dance of chemistry, heat, and engineering precision. The blast furnace, a marvel of industrial engineering, has been a linchpin in the global production of iron and steel for centuries, sustaining and shaping the foundations of modern infrastructure and technological progress. In the steelmaking process, two prominent methods are employed: the basic oxygen furnace, BOF, and the electric arc furnace, EAF. The BOF method utilizes pure oxygen to oxidize impurities in the molten iron, resulting in high-quality steel. On the other hand, the EAF method involves the use of electric arcs to melt scrap steel and adjust the chemical composition as needed. Both methods yield liquid steel, which serves as the foundation for various downstream processes. The subsequent stage, the liquid steel is cast into large slabs or rectangular shapes, which act as the initial form for hot rolling. The slabs are then heated in a reheat furnace to temperatures exceeding 1,700 degrees Celsius, ensuring they reach a malleable state for further shaping. The hot rolling mill, a colossal series of rollers and stands, then comes into play. The heated steel passes through this mill, undergoing successive reductions in thickness and elongation. The high temperatures and intense pressures imparted by the rolling process transform the steel into elongated and thinner coils or sheets, ranging from a few millimeters to several centimeters in thickness. This hot-rolled steel retains a characteristic scale on its surface, a byproduct of the high-temperature rolling process. The scale, while providing a protective layer, is subsequently removed through pickling, where the steel undergoes treatment in an acid bath to eliminate impurities. The resulting hot-rolled coils exhibit unique properties, including a scaly surface texture and a relatively rough finish. Quality control is an integral facet of the hot rolling process, involving continuous monitoring and inspection to ensure that the final product adheres to stringent industry standards. Thickness measurements, surface inspections, and mechanical property testing contribute to the comprehensive quality assurance protocols implemented in modern steel factories. The process of creating cold-rolled steel is a sophisticated transformation that follows the hot rolling stage, enhancing the properties and surface finish of the steel. Hot-rolled steel coils, having undergone the initial shaping and reduction processes in a high-temperature rolling mill, serve as the starting material for cold rolling. The first step in cold rolling involves pickling the hot-rolled coils in an acid solution to remove the mill scale and any oxides that may have formed during the hot rolling process. This pickling stage is essential for achieving a clean surface and improving the steel's weldability. Subsequently, the pickled coils enter the tandem cold rolling mill, where a series of rolling stands progressively reduce the steel's thickness to the desired dimensions. Unlike hot rolling, cold rolling occurs at room temperature, imparting distinct characteristics to the steel. The cold rolling process imparts a smoother surface finish, tighter dimensional tolerances, and enhanced mechanical properties, including increased strength and hardness. Further refinement in the cold rolling process may involve additional treatments, such as annealing. This heat treatment process helps relieve internal stresses and improve the steel's formability. Cold-rolled steel is characterized by its excellent surface quality, uniform thickness, and precise dimensional accuracy. The smooth and shiny finish makes it well-suited for applications where aesthetics and precision are critical, such as in automotive body panels, appliances, and construction materials. The cold rolling process can also produce a variety of steel shapes, including sheets, strips, and coils, tailored to specific industry requirements. Quality control plays a pivotal role throughout the cold rolling process. Advanced inspection techniques, including laser gauges and high-resolution cameras, are employed to monitor and ensure the dimensional accuracy and surface quality of the cold-rolled steel. Stringent testing protocols ascertain that the final product meets the rigorous standards set by the industry. The creation of galvanized and electroplated steel in a steel factory involves specialized coating processes to enhance the durability and corrosion resistance of the steel. For galvanized steel, the initial step is to thoroughly clean and prepare the steel substrate, typically in the form of hot-rolled or cold-rolled coils. These coils then undergo a hot-dip galvanizing process where they are immersed in a bath of molten zinc. The metallurgical reaction between the zinc and the steel results in the formation of a zinc-iron alloy coating, providing a sacrificial layer that shields the steel from corrosion. The galvanized steel emerges with a resilient and uniform coating, making it suitable for a myriad of applications in construction, automotive, and infrastructure. In contrast, the electroplating process is employed for creating electroplated steel, a method that imparts a thin layer of metal onto the steel surface. The steel substrate, often in the form of coils, acts as the cathode in an electrolytic cell, while metal ions from a solution are reduced onto the steel surface, creating a uniform and adherent coating. Commonly used metals for electroplating include zinc and nickel. This electroplated layer not only enhances corrosion resistance, but also introduces specific functional properties, such as improved conductivity or enhanced aesthetic appeal. The precision of the electroplating process allows for tailored applications in industries like electronics, automotive manufacturing, and consumer goods. Both galvanized and electroplated steel exemplify the fusion of metallurgical expertise and advanced coating technologies in the steel factory, resulting in materials that meet diverse industrial demands. The production of metal components is a sophisticated and multifaceted process that unfolds through a sequence of meticulously orchestrated steps, beginning with the selection and processing of raw metal materials. These materials, often in the form of ingots or billets, undergo a rigorous inspection to ensure their adherence to quality standards before initiating the transformative journey. The first stage involves heating the raw metal to a malleable state, typically in a furnace or other heating apparatus. This critical step renders the material more pliable, laying the foundation for subsequent shaping processes. The process of heating raw metal to a plastic state is a foundational step in the intricate world of metalworking, playing a pivotal role in shaping and transforming the material into a malleable form that can be further manipulated to create a variety of components. This critical phase occurs within the controlled environment of a furnace, where carefully calibrated temperatures and precise heating techniques are applied to bring about the desired changes in the metal. The raw metal, typically in the form of ingots or billets, undergoes meticulous scrutiny before entering the furnace. Quality control measures ensure that the material meets specified standards, guaranteeing the integrity of the final product. Once the raw metal is deemed suitable, it is loaded into the furnace, marking the commencement of the thermal transformation. The furnace serves as a crucible of controlled heat, its design and functionality tailored to the specific characteristics of the metal being processed. The selection of the appropriate temperature is a critical aspect of this phase, as it determines the metal's behavior under heat. Various metals and alloys have distinct temperature requirements, and achieving the optimum range is essential for ensuring the success of subsequent manufacturing steps. As the raw metal is subjected to the escalating temperatures within the furnace, it undergoes a metamorphosis from a rigid, unyielding state to a more pliable, plastic condition. This transition is facilitated by the breaking of atomic bonds within the metal lattice structure, allowing the atoms to move more freely. The metal begins to soften, and its internal structure undergoes changes that make it amenable to shaping and deformation. The skilled operators overseeing this process are attuned to the subtle cues of the metal's transformation. They monitor temperature levels with precision, adjusting variables to maintain a delicate balance between achieving the desired plasticity and avoiding undesirable outcomes such as overheating or material degradation. This delicate dance with temperature is a testament to the artistry involved in metallurgy, where the human touch complements scientific precision. The plastic state attained through heating opens a realm of possibilities for shaping the metal into intricate forms. It is at this juncture that the material becomes responsive to external forces, making it amenable to forging, pressing, and other shaping techniques. The ability to mold the metal like clay in the hands of a sculptor marks the beginning of its journey toward becoming a final, refined product. The importance of heating raw metal to a plastic state extends across diverse industries, from automotive manufacturing to aerospace engineering and beyond. It is the gateway to precision engineering, where each nuanced detail of a component is shaped with meticulous care. The plasticity achieved through this process is the foundation upon which the art and science of metalworking build, forging the raw material into the intricate and functional components that define modern manufacturing. In essence, the controlled application of heat transforms the ordinary into the extraordinary, unlocking the latent potential within raw metal and setting the stage for the creation of objects that form the backbone of countless technological advancements. When the metal reaches the desired temperature, the forging process begins. The preheated metal is placed on an anvil, where skilled artisans or sometimes automated machinery apply precise and controlled compression using hammers or presses. This action deforms the metal, shaping it into the desired shape. Forging can be done through a variety of methods including open die forging and closed die forging. Open die forging involves metal being machined between flat dies, allowing for flexible shaping, while closed die forging uses dies of a specific shape, creating more complex and precise components. During the forging process, the metal undergoes plastic deformation, meaning its shape changes without the risk of breaking. This ductility is important for processing materials into complex shapes and achieving desired mechanical properties. Repeated heating and forging cycles refine the metal's grain structure, removing imperfections and enhancing its strength. In the intricate journey of metal fabrication, the metal pressing process serves as a crucial refinement stage following the initial forging. After the raw metal undergoes the transformative heat and force of the forging process, shaping it into a malleable state, the subsequent metal pressing operation imparts a level of precision and intricacy that is paramount for various industries. Metal pressing, often referred to as stamping or forming, involves subjecting the forged metal components to controlled compressive forces between dies. These dies, meticulously designed to match the intended shapes and configurations, exert pressure onto the metal, sculpting it into precise forms. The versatility of metal pressing is noteworthy, as it accommodates a spectrum of complexities, ranging from simple outlines to intricately detailed designs. This process finds widespread use in the automotive sector, where body panels with exact contours and intricate patterns are fashioned with precision. Additionally, the electronics and appliance industries leverage metal pressing to craft casings and components with finely tuned dimensions and specific geometries. The machinery employed in metal pressing is a symphony of engineering precision. Hydraulic or mechanical presses, equipped with specialized dies, exert force uniformly across the metal surface, ensuring consistent shaping. The dies themselves are crafted with meticulous attention to detail, with complex patterns and geometries etched or machined into them. This intricate dance of pressure and precision results in components that not only retain the inherent strength and durability achieved during the forging process, but also exhibit refined contours and specific features. One of the notable advantages of metal pressing is its efficiency in mass production. The process allows for the rapid and consistent production of intricate components, contributing to economies of scale. The high-speed nature of metal pressing operations makes it a preferred method for meeting the demands of industries requiring large quantities of precisely shaped components. The automation potential in metal pressing further enhances its efficiency, minimizing production times and reducing labor costs. Furthermore, the versatility of materials that can undergo metal pressing is a testament to its adaptability. Various metals and alloys, including steel, aluminum, and copper, can be shaped through this process, expanding its applicability across a diverse range of applications. Whether it's creating intricate parts for consumer electronics or forming structural elements for construction. Following the intensive processes of metal forging and pressing, the heat treatment stage emerges as a crucial step, adding a layer of refinement to the components. Heat treatment is a controlled thermal process that imparts specific mechanical and metallurgical properties to the metal, ensuring enhanced strength, hardness, and durability. Once the metal components have undergone the shaping and compressive forces of forging and pressing, they enter the heat treatment furnace. The goal is to subject the metal to carefully controlled heating and cooling cycles, known as annealing, quenching, and tempering, tailored to the material's composition and the desired properties. Annealing involves heating the metal to a specific temperature and allowing it to cool slowly, relieving internal stresses and refining the grain structure. Quenching, on the other hand, involves rapid cooling to harden the metal, while tempering follows, reheating the metal to a controlled temperature to achieve a balance of hardness and toughness. This meticulous orchestration of temperature changes results in a metallurgical transformation, optimizing the mechanical properties of the metal components. The heat treatment process is a critical enabler for components destined for applications demanding exceptional strength and resilience, such as automotive parts, aerospace components, and industrial machinery. It not only ensures the longevity and reliability of the final products, but also exemplifies the synthesis of scientific precision and traditional craftsmanship in the realm of metallurgy. Grinding, an abrasive machining process, introduces precision and smoothness to the metal surfaces. This step is instrumental in refining the dimensions, tolerances, and surface finish of components. Grinding wheels, composed of abrasive particles, remove excess material with remarkable accuracy, ensuring that the final product adheres to exact specifications. The intricacy of this process lies in the finesse with which material is removed, creating surfaces that meet the highest quality standards. Turning, executed on lathes, represents a pinnacle in the manufacturing process, where raw metal components are shaped and carved into their final forms. Lathes, whether conventional or computer numerical control (CNC), offer unparalleled versatility in shaping metal. Skilled machinists adeptly manipulate cutting tools against rotating workpieces, chiseling away layers to achieve the desired contours. This stage is not merely about creating shapes. It is an art form where precision, accuracy, and attention to detail converge to produce components that seamlessly integrate into complex assemblies. The amalgamation of these diverse processes culminates in the creation of final products, exhibiting a kaleidoscope of shapes and functionalities. Whether it be intricate gears for machinery, structurally resilient components for aerospace applications, or aesthetically refined architectural elements, each product reflects the culmination of a journey through the crucible of metal fabrication. The production of electric motors is a multifaceted process that involves intricate engineering and precise manufacturing to meet the diverse demands of both industrial and household applications. In the realm of industrial electric motors, the manufacturing process begins with the selection of high-quality materials, including specialized alloys, laminated steel cores, and copper windings. These components are crucial for ensuring the motor's efficiency, durability, and overall performance. The winding process follows, where copper or aluminum coils are meticulously wound around the stator, creating the electromagnetic field that drives the motor's rotation. The stator and rotor, the core components of the motor, undergo precision machining to achieve tight tolerances, enabling seamless interaction within the motor housing. In parallel, the housing, typically made of durable materials like cast iron or aluminum, is formed to protect and encase the intricate internal components. For industrial electric motors, customization plays a pivotal role. Depending on the application, motors may vary in size, power ratings, and features. Advanced manufacturing technologies, such as computer numerical control, CNC machining, are employed to ensure consistency and precision in the production of components. After assembly, the motors undergo rigorous testing, including performance evaluations, thermal analysis, and efficiency assessments, to guarantee they meet stringent industry standards. Household electric motors, designed for a myriad of applications, undergo a similar yet often more streamlined manufacturing process. Components are meticulously crafted for efficiency and cost-effectiveness, and the assembly process is optimized for mass production. For example, electric motors in appliances like blenders or washing machines require a balance between power and compact design. These motors often feature simplified construction compared to their industrial counterparts, focusing on reliability and energy efficiency within the constraints of household applications. In both industrial and household electric motor production, adherence to energy efficiency standards is paramount. Modern electric motors are designed with a keen focus on reducing energy consumption and environmental impact. Innovations such as variable frequency drives, VFDs, and permanent magnet motors contribute to improved efficiency and performance. Aligning with global initiatives to promote sustainability, the production of electric motors is a dynamic interplay of materials science, precision engineering, and technological innovation. From the industrial powerhouse driving large-scale machinery to the unassuming motor humming quietly in household appliances, each motor is a testament to the seamless integration of cutting-edge manufacturing techniques and a commitment to creating reliable, efficient, and environmentally conscious technology. As industries evolve and energy demands shift, the production of electric motors continues to adapt, pushing the boundaries of what is possible in the world of electromechanical engineering. Within the specialized workshop dedicated to crafting the GE90 and GE-NX composite fan blades, a convergence of advanced technologies and precision manufacturing processes unfolds. This aerospace manufacturing facility is designed with a meticulous focus on achieving unparalleled strength, performance, and efficiency in the production of fan blades that power some of the world's most powerful jet engines. The process commences with the careful selection of aerospace-grade materials, including high-strength carbon fiber-reinforced composites and advanced epoxy resins. These materials, chosen for their exceptional properties, undergo rigorous quality checks before being subjected to intricate layup processes. Skilled technicians, equipped with extensive knowledge in composite manufacturing, meticulously layer the materials to ensure optimal fiber alignment, a critical factor for achieving the desired mechanical characteristics. The heart of the workshop houses state-of-the-art CNC machines and robotic systems, which play a pivotal role in shaping the composite materials into the intricate profiles of the fan blades. Computer numerical control, CNC machining, allows for micron-level precision, enabling the creation of blades with uniform geometries and structural integrity. These machines operate with a level of sophistication that is calibrated to meet the exacting specifications demanded by the aerospace industry, ensuring consistency across the entire production line. The manufacturing process extends beyond shaping the blades. It encompasses intricate operations such as drilling cooling holes and attaching root fittings. These processes are critical for optimizing the blade's aerodynamic efficiency, structural integrity, and overall performance. The workshop seamlessly integrates traditional craftsmanship with automated precision, creating a synergy that addresses the complexity and scalability required for manufacturing fan blades on a global scale. Quality control within the workshop is rigorous and employs cutting-edge technologies. Non-destructive testing (NDT) methods, such as ultrasonic and X-ray inspections, are employed to scrutinize each blade for internal defects. High-resolution imaging systems capture detailed visual data, while dimensional checks verify that each blade adheres to the precise tolerances set by design specifications. This stringent quality assurance process ensures that only flawless blades progress through the production pipeline, upholding the highest safety and performance standards mandated for aerospace components. The workshop also places a strong emphasis on environmental sustainability. The composite materials utilized in the fan blades contribute to the engine's overall fuel efficiency, reducing environmental impact through lower fuel consumption and emissions. Additionally, waste reduction and recycling practices are integral to the workshop's operations, aligning with broader industry initiatives for sustainable aerospace manufacturing. In conclusion, the workshop dedicated to crafting the GE90 and GE-NX composite fan blades stands as a paragon of advanced manufacturing in the aerospace sector. From material selection to precision machining, from traditional craftsmanship to cutting-edge automation, every aspect of the workshop's operations is calibrated to produce fan blades that exemplify the pinnacle of aerodynamic efficiency, structural integrity, and environmental responsibility. As it continues to propel the aviation industry forward, this workshop embodies the intersection of technology and craftsmanship, shaping the future of jet engine technology.